is the 5th lecture and we start BJT biasing and bias stability. That biasing is a very important phenomenon for using a device as an amplifier can hardly be overemphasized, and the discussion we shall make with regard to a common emitter amplifier, but the principles shall be applicable everywhere. A common emitter BJT amplifier, typical circuit is this: you have an RE, and RE is usually bypassed to ground by a capacitor CE. The collector is connected to a resistance R sub C, collector resistance, that goes to a power supply plus VCC, and the base biasing, the base current is provided from the same supply with two resistances with a potential divider. We call, traditionally we call this resistance as R1 and this resistance as R2. Obviously this is an NPN transistor, and the signal is applied, the signal to be amplified is applied through a capacitor C1 to the base circuit. This is the signal to be amplified, Vs, and the output is taken from the collector through a decoupling capacitor C2 to whatever the load is, R sub L. So this is Vs and this is the AC or the signal output. You know the purpose of these two capacitors C1 and C2 are to decouple DC from AC. What we want is that the DC from here should not pass through the signal source. You see, what is the internal resistance of this source? If it's a voltage generator, then the internal resistance is 0. Say it loud. Why are you so afraid? If you are wrong, I'll correct you. Okay. So if this capacitor is not there, then obviously R2 will be short circuited. Isn't that right? If this capacitor is not there, the internal resistance of the source is 0, therefore R2 will be short circuited, and therefore the base will be connected to ground, and the transistor would be off. It cannot be in the active region. So the capacitor C1 decouples DC being short circuited. Sorry. If the capacitor C2 is not there, then the current through R sub C will partly flow through the collector and partly through RL. We don't want that. For example, this RL could be a loudspeaker. The load could be a loudspeaker. If it is an amplifier, audio amplifier, it could be a loudspeaker. If it is a loudspeaker and the DC passes through the loudspeaker, the magnet may get into saturation, and therefore it may not respond to the signal. Okay, we don't want DC to pass through the load. Also, if the load varies, then the collector current shall also vary. If RL varies, then the proportion by which IC and IL change, that will change, and therefore the biasing point shall also change. So this is a decoupling capacitor, this is another decoupling capacitor. These are facts of life, you have to use them.
So could you please repeat the functions of C1 and C2?
The functions of C1 and C2. C1 prevents DC flowing through the signal source, and C2 prevents DC flowing to the actual load. That's it. They decouple DC from AC. And the purpose of CE, the third capacitor, across the emitter resistance, is to act as a short circuit to AC. As far as DC is concerned, RE is effective. There is a drop in RE. But as far as AC is concerned, we don't want any drop in RE. So we bypass RE by a large capacitor. If 1 by omega CE, the reactance of the capacitor, is much less than RE, then whatever AC comes from the emitter will flow through CE, not through RE. So CE is effectively an emitter short circuit. Okay, it is a short circuit to RE, it is also called a bypass capacitor. That is, AC does not flow through RE, it flows to the bypass. It's called a bypass capacitor. Yeah.
What is the use of RL in this? We can directly take the input from the terminal G0.
Then DC as well as AC will come.
No. If we connect a capacitor and we don't connect RL, and we take this
Oh,
directly.
the RL is not a matter of choice, it's fixed. For example, if say audio amplifier, RL is the loudspeaker. You have to pass the AC through the loudspeaker in order to reproduce the sound. It's not a choice, it's not your choice. Okay? It could be that the output is open circuit, that is the load is infinite. For example, if I apply this to an oscilloscope, well, the effective input impedance is infinity, and therefore it could be open circuit. RL is not your choice. RL is dictated. Okay? Now, the point is, in order that this may act as a good amplifier, you must choose these two quantities carefully. That is, one is VCE and the other is the collector current I sub C. VCE and I sub C, these define the operating point of the transistor, and this operating point must be chosen carefully. Let's look at the DC model of this amplifier and then see where should the operating point be. If you notice carefully, as far as DC is concerned, we can forget about C1 and Vs. DC is not affected by this. We can forget about CE. We can forget about C2 and RL. Therefore, as far as DC is concerned, all that we have to consider is this resistance. Let me use some other color. All that we have to consider is this part of the circuit. Okay? The rest of the circuit can be ignored as far as DC is concerned. Also, you notice that VCC, the voltage source, is applied across R1 and R2. It is a potential divider. So, if I apply Thevenin's theorem to the left of this line, I can replace VCC, R1 and R2 by an equivalent voltage source, which is VCC R2 divided by R1 plus R2, open circuit voltage source, and the effective resistance looking back, which is R1 parallel R2. Alright. So, if I do that, then my equivalent circuit shall be VBB, which is equal to VCC times R2 divided by R1 plus R2. Okay. This is the Thevenin source. Then a resistance R sub B, which is R1 parallel R2. Okay. Then we come to the base terminal. From the base to the emitter, in the active region, you know there is a drop of 0.7 volt. So, let us call this as VBE, 0.7, the numerical value will come to later. This comes to the emitter. We are considering the active region, so we are not using the diode. Ideal diode is a short circuit anyway. Okay. The transistor is in the active region, and therefore all that happens is there is a drop VBE. This is the emitter terminal. Emitter goes to ground through the resistance RE. This is effective in DC, and as far as the collector circuit is concerned, what we have is I sub C, which is equal to beta IB. If this current is IB, then beta IB plus beta plus 1 ICO. ICO sometimes we call ICBO. Alright, ICBO. So, beta plus 1 ICBO, and you also know that beta plus 1 ICBO we denote by ICEO. So, let us denote it by ICEO. This is the current generator, this is the effective collector current, and we of course have the resistance R sub C, which goes to not ground, it is the DC model. I wanted you to make this mistake, yes, it was intentional. VCC, so this is VCC plus minus, that goes to ground, the negative terminal. Okay. So, this is my DC model of the common emitter, PNP transistor amplifier. And now there are two loops in this circuit. I can write one loop equation here and the other loop equation here. Okay, let's look at this loop equation, the first loop, the loop to the left. You notice that I can write VBB as equal to I sub B times R sub B. This is the drop in the resistance RB, which is the parallel combination of R1 and R2, plus VBE plus the current through RE. Let's look at this current. This current is the sum of IB and this current, beta IB plus ICEO. All right. So the current is beta plus 1 IB, okay, beta IB and IB from the left and beta IB from the right, plus ICEO multiplied by RE. This is the base current. This is the left loop equation, which gives you a base current as equal to, if you solve for base current, it would be simply VBB minus VBE. This term goes to the left, and what else? Minus ICEO RE divided by RB plus beta plus 1 RE. This is the base current. All right. We will see later on, in order to find out I sub C. Can we find I sub C from here? I sub C is beta IB plus ICEO. Okay, and therefore if I substitute beta IB from here, I can get an expression for I sub C. I will write this expression later because I shall need that. All right. And usually what I will do is, when I write an expression for I sub C, I will go back to ICBO. That is, instead of ICEO, I will write beta plus 1 ICBO. Okay. This is a sideline. We don't need this equation now, but we will require this later on. We shall have to utilize this expression for I sub B. On the right loop, if you notice, I have VCE, okay, this voltage from here to here, VCE. VCE would be VCC minus this drop in R sub C, which is IC RC, and then the drop across RE, which also we have found out. Therefore, my VCE should be equal to VCC minus I sub C R sub C minus I sub C plus I sub B. I want to write this expression in terms of I sub C. All right. So I don't write beta plus 1 IB plus ICEO. Instead, I write I sub C plus I sub B times RE. And in this, I substitute, I want to write this expression in terms of I sub C only. I don't want I sub B. So what I do is I write I sub C equal to beta I sub B plus beta plus 1 ICBO, which means that I sub B I substitute in this as I sub C minus beta plus 1 ICBO divided by beta. Agreed? And this expression I substitute here. This expression for IB, you see IB now contains IC and some parameters of the transistor. If I do that, then I can simplify VCE, I leave the algebra to you, as VCC minus I sub C R sub C plus RE 1 plus 1 over beta plus ICBO times beta plus 1 divided by beta times what? RE, I think so. IB multiplied, yes, that is correct. So this is my equation. Is the whole equation visible on the monitor? Whole equation including this part?
Yes.
Okay, fine. Now a couple of comments before we go to the next point for consideration. Couple of comments. You know, normally beta is much greater than 1. Beta is of the order of 100, and therefore 1 plus 1 by beta, approximately you can ignore this term. You can ignore this term, 1 by beta. It will be 0.01 at 1% of this term. Similarly, beta plus 1 by beta you can take approximately as 1. Not just that, ICBO you know is of the order of a nanoampere, tens of nanoamperes, and RE is of the order of a K, and therefore this whole term is very, very small, and therefore you can approximate this by VCC minus I sub C R sub C plus RE. Agreed?
Yes.
And this equation describes what is known as the DC load line. DC load line. At DC, the load of the transistor is equivalent load is RC plus RE. They don't exactly add to each other. They add with the factor 1 plus 1 by beta, but because beta is very large, one can take the total load to be RC plus RE, and this equation describes the collector emitter voltage VCE and the operating current I sub C in terms of constants in the circuit, namely VCC and the total load resistance. So this is called a DC load line. We shall see what the import of the DC load line is, but before that let's take a small example. And this example we shall we shall continue to take the same example again and again to illustrate the points. It's a typical common emitter PNP transistor amplifier. The plus VCC is 12 volt, beta is equal to 100, VBE is given as 0.6 volt for a change, 0.6 volt, ICBO is given as 10 nanoamperes, which is equal to 10 to the power minus 10 to the minus 8 ampere. This is given. R1 and R2 both are 6.8K, 6.8K, and RE and RC both are 100 ohms. Suppose this is the circuit, all right. We are required to find out the operating point of the transistor. Okay, the first thing one does is one uses the relation for IB, and you remember that I sub B is equal to VBB minus VBE, what else? Minus ICBO times beta plus 1 times RE divided by RB plus beta plus 1 RE. If you substitute this 6, VBB would be 6 volt now, VCC R1 R2 divided by R1 plus R2 minus 0.6 minus 10 to the minus 8, beta plus 1 is 101, RE is 100. Even with this is of the order of 10 to the minus 4. Isn't that right?
Yes, sir.
Therefore, it can be ignored. Okay. Divided by RB is 3400 ohms. RB is the parallel combination of 6.8K and 6.8K. So, it is 3.4K, 3400 ohms plus 100 multiplied by 101. Agreed? Okay, so this comes out as 0.4 milliampere, which means that I sub c, if this is 0.4 milliampere, then I sub c is beta times this, that is 40 milliampere plus beta plus 1 ICBO, which is negligible, okay, and therefore it is 40 milliampere. You see, in this relationship IB equal to 0.4 milliamps and IC equal to 40 milliamps, the effect of ICBO is negligible because ICBO itself is very, very small. Okay, it's a good transistor. 10 nanoampere ICBO is a good transistor. Now, if you know I sub c, naturally then you can find out VCE. VCE is, yes, VCC minus
IC times RC plus RE. IC times RC.
That's right, and IC times RC plus RE. We have ignored that beta 1 by beta term and also beta plus 1 by beta and then the whole ICBO term. It must be understood, because in a lousy transistor where ICBO is not that small, you have to consider the effect of that. All right. Also, if the temperature rises, you know, ICBO, I told you that the reverse saturation current of a diode approximately doubles for every 10 degrees centigrade rise in temperature, and therefore if there is a rise in temperature, you might have to consider ICBO. For example, if the rise in temperature is, let's say, by 100 degrees C, room temperature is 25, suppose the temperature is raised to 125, then ICBO will multiply by 2 to the power 10. Is that clear? We will consider such an example later. Now, in this particular case, this is 12, IC is 40 milliampere multiplied by 200 ohms. So, this is equal to 4 volts. Okay. So, this is my operating point. Operating point is VCE equal to 4 volt and I sub C equal to 40 milliamps. Now, let us look at this operating point. I am tempted to, alright, this is the operating point. Now, I have a slight temptation which I want to discuss, a little bit of detour. You see, all that I need to make this into an amplifier, last bench, all this I need to make it into an amplifier is to connect a voltage source here and connect a load here. Okay, that's all that I need. Now, if I want to draw the AC equivalent circuit, all right, what we shall have is the source Vs, the capacitors C1 and C2. I also need to connect a bypass here, CE. The capacitors C1 and C2 are so large that at the signal frequency they will act as short circuits. Similarly, CE will also act as a short circuit. So, in the AC equivalent circuit, the emitter shall be virtually grounded. Yes.
Why don't you want any drop in the RE in case of an
Okay. If there is a drop in RE, then it causes a loss of gain. It acts as a negative feedback, as we shall see later. We don't want this. We want as much gain as possible, unless it is intentional. Sometimes it is intentional. Sometimes negative feedback is used intentionally to stabilize the amplifier, but normally we don't want it, we want to bypass it. Okay. So, RE will be short circuited, in other words the emitter itself shall go to ground. Between the base and emitter I shall have the parallel combination of 6.8K and 6.8K. Is that right? Between this point and the emitter or ground, at AC this point will be virtually grounded. So, between this point and ground we shall have 6.8K and 6.8K in parallel, because the battery is virtually grounded, AC grounded. Okay. So, that would be equivalent to 3.4K. Then from here to here I shall have Rx plus R pi, and the current that flows would be small I subscript small b. Okay. Then I come to the collector side. In the collector side only the current generator beta times IB shall remain, alright, and in parallel with RC and RL. RC and RL shall be parallel. So this small discussion should convince you that my AC equivalent circuit would be like this: Vs, then I shall have R sub B, which is a parallel combination of R1 and R2. Let me indicate this: R1 parallel R2. Then I shall have Rx, which is the base spreading resistance, and R pi. This current is I sub B. This current is I sub B, and then on the other side I shall have the current generator from the collector. This is the collector. From the collector I shall have beta times I sub B, okay, beta times I sub B, then in parallel with RC parallel RL. Alright, let us call this resistance as RL prime, and this value, this voltage therefore is the output voltage, and as you see this is the voltage between small v, voltage between the collector and the emitter, and since this is AC we write this as VCE plus minus. Agreed? This point is the collector and the emitter has been grounded, so the output voltage is the incremental part of collector emitter voltage. And since this is the AC voltage, we use a symbol small v, small c, small e. Agreed? And this is the collector current, AC collector current, which is small I subscript small c. Okay. What is the relationship between this voltage, this current and this voltage? Isn't this simply VCE as equal to, yes, minus IC times RL prime? Agreed? We will require this relationship a little later. We will require this relationship. There is a negative sign because there is a phase change. Alright? There is a negative sign, minus IC. RL prime is the parallel combination of RC and RL. This in fact we brought this in because this equation describes the AC load line. The DC load line had RC plus RE as the load, DC load. The AC load is RC parallel RL, so it is RL prime, alright, and this is the relationship. VCE is equal to minus IC times RL prime. We will require this in a few moments. Now let us look at this figure, which shows the limits on operation of the common emitter transistor amplifier. I want a different color, the green one shall do. Okay. These are the transistor characteristics. This yellow, light yellow shaded curves, these are the transistor characteristics, typical BJT characteristics. As you can see, they are approximately parallel to each other and they are approximately equidistant. That is, from 500 to 600 the increase is about 10 milliamperes. From 500 to 400, 500 is the base current. This is the base current. From 500 to 400 the difference is approximately again 10 milliamperes. Okay. I sub C, this is a plot of I sub C versus VCE. Okay. This is a plot of IC versus VC. This line is the saturation line. So our amplifier operation should never go below this line. Alright. Now there is another line which restricts the operation of a transistor, and this is what I want to introduce at this moment. You see, VCE and I sub C, they denote the operating point of the transistor. Now, if you maintain a voltage VCE in a device across two terminals through which a current I sub C flows, obviously the product VCE times IC, this much power is absorbed by the device, alright, and this power is dissipated in the device. How is it dissipated? The transistor gets heated. It gets dissipated in the form of heat. Now, if the heat is excessive, then the junction temperatures rise, and if temperatures rise, three things happen. Beta changes approximately 50% for a 100 degree centigrade rise in temperature. Beta changes. If beta changes, it increases. With temperature rise, beta increases. Now, if beta increases, then naturally the collector current again increases. Isn't that right? If IB remains the same, then the collector current is beta times IB, so it increases. If it increases, it causes more dissipation, and therefore the transistor temperature goes higher up, and this is a regenerative process. That means it is a vicious circle. Ultimately, unless you put off the power supply, the transistor will be burned. This phenomenon is called thermal runaway. Thermal, RUNAWAY, run away. The transistor ultimately gets destroyed. Therefore,
repeat this once more, sir,
this heating effect. Okay. If the transistor is heated, because of an excessive current going to the transistor, then the junction temperature rises, and if the junction temperature rises, three things happen. Beta increases, VBE decreases, ICBO. What happens to ICBO? Increases. Okay. Beta, these rates are, beta approximately changes 50% for every 100 degrees centigrade rise in temperature. That is, if beta was 100 and the temperature is raised by 100 degrees C, then beta will become 150. If beta increases, well, the other two are VBE decreases at the rate of, I told you, VD, dVD dt in the first lecture itself, 2.5 millivolt per degree C. VBE decreases by 2.5 millivolt per degree C. This is rule of thumb. Okay, and ICBO doubles for every 10 degrees centigrade rise of temperature. But the most harmful effect is that of increasing beta. If beta increases, I sub C, which is beta times IB, increases, causes further dissipation, further heat generation, and therefore, and this is a regenerative process, the transistor cannot come out of it. Ultimately, more heat, more IC, more heat, and ultimately the transistor gets burnt up, and this phenomenon is called thermal runaway. Therefore, there must be, all manufacturers say your VCE and IC must be such that the maximum power dissipation allowed is not exceeded, and for this transistor, which is a 2N222 transistor, the PD max is 500 milliwatt. This is specified by the manufacturer. Therefore, you draw a curve on IC VCE such that the product IC VCE is 500 milliwatt. Obviously, this would be a hyperbola.
So, how do we calculate this power dissipation of the transistor? Is it simply VCE into IC?
It is VCE into IC plus VBE times IB, but normally IB is 100 times, beta times less, and therefore that dissipation is negligible compared to the collector junction dissipation. We normally take VCE times IC. Now, on this characteristic, if you plot VCE times IC equal to PD max, there is a maximum allowable power dissipation, you get a hyperbola. So, your operating point must be on the left side of this hyperbola. Is the point clear? This light brown shaded hyperbola, This is the PD max curve. And do you understand how this is plotted? It is simply VCE times I sub C is equal to PD max. All right. So your operation must be to the left of this line, left of this hyperbola. Your operation must be to the right of this saturation line. So you are gradually constraining. In addition, there are other constraints. For example, you cannot increase VCE beyond a certain limit. What happens? There occurs a breakdown. And this breakdown for this particular transistor occurs at about 30 volt. So 12 volt is a safe limit. Okay, you can't apply a VCC of, let's say, 100 volt. Then in all probability the transistor will break down. Okay, so there is a vertical line here. There is a vertical line which restricts not only PD max curve, but there is a vertical line occurring at VCE max. This will also be specified by the manufacturers. Sometimes it is specified as breakdown collector voltage. There are various terms, but you should understand. Similarly, the current that can be drawn from a transistor, there is an absolute limit. There is a limit. You cannot draw more than that. So there would be a vertical line somewhere here. For this transistor, this is 800 milliamps. And our operation normally will be restricted to about 1/10 or 1/8 of this, about 100 milliamps. We will not draw more than that. So you see, the operation, the Q point of a transistor must lie between several, is bounded by several limits. One is PD, then you have the saturation line, you have the vertical line, collector breakdown, limited by collector breakdown, you have a horizontal line limited by the maximum allowable collector current. This is the IC max, this is PD max, this line is saturation, this line is decided by breakdown, and what about the other dimension? We have cutoff. Cutoff is obviously this line, right? So cutoff. Your Q point must lie in this shaded region. Your Q point should not lie outside this. Also, to be able to operate this as a good amplifier with a reasonably good dynamic range, that is, if you want a large signal operation, then your Q point must be somewhere well inside the region, isn't it? It should not be too close to the cutoff. It should not be too close to saturation. It should not be too close to PD max curve. It should not be too close to breakdown or the IC max. It must be well inside this. Is the point clear?
Yes.
The general principle that Q point must be well inside this region. Now what is the best? What is the best? That depends on the situation. Let's look at the present example. In the present example, this light violet colored line joining Q1, Q2, Q3 is the DC load line. You see, DC load line, as I had told you, the equation to the DC load line, what is the equation? VCE is equal to 12 I sub C multiplied by, which is 200 ohms here. Alright. So if IC is 0, VCE is 12 volt. Alright. And if VCE is 0, then IC is how much? 60 milliampere. Agreed? So to draw one straight line, 2 points are enough. These are the 2 points. You see, 12 volt and 0 current, 60 milliampere and 0 voltage. So you join these two, then this is the DC load line. Okay. We have also found out the Q point or the operating point. The operating point was 4 volt and 40 milliamps. So Q1 is the operating point. Is the point clear? The operating point clear? Point about the operating point?
No, sir.
No. Is the load line clear?
Yes.
Okay, we had already found out that I sub C, with the kind of biasing that we had found out for that example, the collector current was 40 milliamps and the collector emitter voltage was 4 volts. So draw a vertical line at 4 volt and draw a horizontal line at 40 milliamps where the meet is the operating point. So Q1 is our operating point. Alright. Now if Q1 is the operating point and this is the DC load line, okay, and we are working as, now is Q1 a reasonably good operating point? Yes, it's well inside, but let's see how it behaves in the face of AC, in the face of a signal. Okay, if there is signal, then you know the DC load line is not enough. We have to draw the AC load line. An AC load line from the AC equivalent circuit. We have already seen that the AC load line is VC equal to minus I sub C small c RL prime. I can write this as I sub C as minus VCE divided by RL prime.
So, you said VC is the increment. Could you please repeat that? Elaborate on this.
VC is the AC signal. That means it is the perturbation. Well, as I have said, the total collector emitter voltage is equal to VCE, the DC voltage, plus small v, small c, small e. So this is an increment on the DC collector voltage. Okay. In order to bring this into the picture, I write this as capital C, total collector current, minus capital I subscript capital C. Alright, this is the value of IC, that is equal to minus 1 over RL prime. VCE can be written as total collector emitter voltage minus VCE. And in order to emphasize that this is an increment over the Q point or the operating point is also called the Q point, I will introduce the additional symbol Q here. That is IC minus ICQ equal to VCE minus VCEQ divided by RL prime. One thing is obvious, that this is the AC load line. AC load line. Significance of Q, or the operating point is sometimes called the Q point, and therefore our amplifier operates around this point. That is, the signal excursions on either side of this point. Signal excursions are on either side of this point. If the signal goes up, the collector current goes up. If the signal goes down, the collector current goes down. Okay. So I have used the additional symbol Q here to emphasize that amplifier operation is around that particular operating point. This is the equation to the AC load line, and one of the things that is obvious is that it is a straight line, isn't it right? Y equal to mx plus c. Y is your total collector current and the slope is minus 1 by RL prime. This slope obviously is greater than the slope of the DC load line. What is the slope of the DC load line? Minus 1 by RC plus RE, and RL prime is less than RC. Therefore, the slope of the AC load line is greater than the slope of the DC load line. Is that point clear? And the second thing is that the AC load line must pass through the Q point. Why? Because when VCE is equal to VCEQ, I sub C must be equal to ICQ. Isn't it right? So the AC load line must pass through the Q point. And this blue line is the AC load line. As you can see, its slope is minus 1 by, what is the value here? 100 ohms and Did I mention what the load is? Oh, load I didn't mention. Take the load as 100 ohms. RC was 100 ohms. Take this also as equal to RL. Then the slope of this line is minus 1 by the DC load line, minus 1 by 200. The slope of this line is minus 1 by 50. So if you know the slope and one point on the line, you can draw the line. This is the AC load line, okay, and you can see that the particular transistor can now act as an amplifier in which the excursion of AC voltage is limited to how much? Can you see this figure? This is 4 and the AC load line touches the cutoff line at 6. So the peak value of the AC signal cannot exceed 6 volts. No, I am sorry, 2 volts, 4 to 6. And on the lower side it goes from 4 to 2. Does it come to the saturation? No. So it's a safe operation, alright. 2 volts, which means 4 volts peak to peak. Can I repeat? Okay. You see, as far as this, if this is the AC load line, then AC voltage, the total voltage on the collector, when the AC input is 0, total voltage is simply 4 volt. If the AC input is increased, then the collector emitter voltage increases and the maximum increase permitted is 6 volts. Maximum VCE permitted is 6 volts. So the excursion, that is the perturbation or deviation from the Q point, is 2 volts on this side. Naturally it can come 2 volts on the other side also. So the peak to peak voltage is 4 volts. That is the excursion. On the other hand, the current, what about the current? 40 milliampere is the Q point. The current can go right up to 0 and the current can go right up to, on the other side, 100 milliampere. But then if you want symmetrical swing, you should be limited to 80. That's right. So between 0 and 80. So this is a very good operating point. It's quite far away from PD max, so you are safe. It's far away from 30 volt. It's the current 40 milliampere is far away from 800 milliamps. So this denotes the AC load line and a safe operating point. There are two other operating points which are sketched in this figure. One is Q2 and the other is Q3. Suppose our operating point is here, then obviously the same AC load line, obviously the voltage swing would be very limited, would be very small. Not only that, this has come close to the cutoff, it has come close to PD max, it has come closer to 30 volt. Okay, so this is not a good operating point. Similarly, Q3 is also a bad operating point, because if you go slightly to the left you get the saturation line, alright, and therefore the signal range would be very limited. And as I said, the operating point should be somewhere in the middle of that peculiar shaped closed diagram, and Q1 in this case is a good operating point. Now that's not enough. To set an operating point has to be done. I mean, there is no other way. It has to be done. You have to set a good op. You have also to make sure that this operating point is not disturbed by external changes. For example, not power going off, but suppose the power fluctuates from 230 volt. It sometimes go right up to 320 or goes down to 110. Then the power supply, you know, this battery, you don't actually use a battery, you use a power supply. The power supply voltage shall also fluctuate. Say instead of 12 volt it goes to 11 or 10 volts. Then obviously the operating point will have a tendency to change. Wait a second, it will not allow it to change. We will design this circuit in such a manner that the change that happens is negligible. We have to do that. Otherwise, suppose due to a power supply fluctuation the operating point goes to Q3, then your transistor amplifier is gone. I mean, it will not be able to act as an amplifier in the context that you were using earlier. Number 2, if the temperature goes up, let us say a circuit which we want to operate in summer as well as winter, there is a large range of temperature change. Delhi, it comes down to 0 and the highest goes to about 50, 47, 46, it's quite common. And if there is a large change of temperature, as I said, beta changes, VBE changes, I sub CBO changes, and therefore again the operating point shall change. Okay. Number 3, which is most usual, suppose due to some reason the transistor goes bad, you have to replace the transistor. It may be the same type of transistor 2 and 2 to 2, but the parameters will vary. This is one of the bad things about transistors, that they have a large spread. You know what is spread? Spread is maximum divided by minimum. For example, if you take a simple transistor whose nominal value manufacturer specifies 100 beta, manufacturers will also say min, tip, max, minimum, typical, maximum. Minimum they will specify 50. That means their process, the technology is such that no transistor beta less than 50 will be fabricated. Okay. So they say minimum 50, maximum maybe 150. So the spread is 3 and the typical value is 100. So if you take out a transistor and replace with another, immediately the Q point shall change. Not only beta is the maximum culprit, not only beta, but there may be a small change in VBE and ICBO also, because from transistor to transistor, even with identical process, for example 1 hour of oxidation, another hour of nitrification and so on, with all the process steps exactly identical, even then the values change, because semiconductor material is such that exact identical features cannot be maintained, and therefore if there is a replacement of a transistor, we want to make sure that Q1, the Q point remains at Q1, and this process, this step is called stabilization. Not only we want to establish two terms, establishment and stabilization. Not only we want to establish an operating point under the present conditions, we also want to make it a stable operating point, that is, despite provocations of temperature change, replacement of transistor and so on and so forth, despite all provocations, Q1 should at the most change to Q1 plus delta Q1, where delta Q1 tends to 0. So we will look at the various aspects of stabilization next time on Monday.